Hi everybody and welcome back to the channel. This week we're going to look at something that's been something of a hot topic in exercise physiology for a while now, critical power. It's very heavily used, it's very heavily investigated, and it's often misinterpreted or misrepresented in its physiological basis. So what I'd like to do for this particular presentation is go through how we got to the point where we were measuring critical power and how we actually go about doing it. So we're going to take a little bit of a historical bent and then move on to how we can actually characterize the power duration relationship in its most basic form. Well, here is a power duration relationship, or more specifically a speed duration relationship in its most basic form. So these are the current world records for athletic events up to and including the marathon. And you can see there's a very characteristic curve shape. It declines very rapidly initially, then it turns a corner, and then it seems to be plateauing out. So this sort of curve shape led to people saying, well, what's the physiology underneath that? Or what's the mechanics underneath that? What scientifically creates this human performance envelope? And there have been a number of approaches to this. One of them that I'm not going to talk about today is the use of exponential modeling to describe this, because I've talked about exponentials enough in previous presentations. But there are other formulations that in and of themselves have quite an interesting history behind them and quite a lot of interesting application. And so this nonlinear power or speed duration relationship can be modeled in several ways. And the first way it was done was with power law scaling. And this is Kennelly in 1906. What he was looking at was various athletic performances for swimming, for walking, for rowing, and for running, and also for skating, and then trotting and presumably cantering or galloping in horses. And what you see on these lines, well, I say what you can see, you can't really see them very clearly because he's not the greatest figure in the world, but what you can glean from this is these downward sloping lines are the speed duration lines. These upward sloping ones are the time distance lines. So they're the same data, they're just plotted in different ways. But the key point of the plot is that they are on log axes. And so you have a straight line, or you can create a straight line relationship by logging both axes, and that's the basis of a power law function. So in a power law function, you have a proportionality constant relating x to y, and then you have an exponent. So this is an alpha exponent. And in this case, the relationship, or in this case, the slope of the line, depends entirely on the exponent alpha in this case. And power law functions have this special property of being scale invariant, and therefore you can fit an enormous range of data, potentially across several orders of magnitude. So a power law function is special because it has the potential to essentially characterize every record or every human performance from maximal sprinting all the way through to, indeed polar exploration if you really wanted to. This scale invariance is even more interesting when you consider how it plays out in nature, and we can start to think about fractals and things like that. And the reason this is interesting is because if you take the lung, for example, the lung is scale invariant. So what you have here with the trachea and the bronchi and the parabronchi is essentially a tube that then branches and then grows again, and then branches and grows again, and carries on and carries on. Whatever scale you look at, you will see something that looks similar to the scale above it until we get all the way down to the alveoli. And this is a really efficient way of building things in nature, and you see it all over the place because all you need is two instructions. Make a tube and then branch it now and again, and you can produce all kinds of really intricate structures. This is how we grow blood vessels, this is how we grow the lung, muscle as well is of this nature. So it'd be really interesting if this also played out in the sense of human performance in a macroscopic sense. And this has been tried. So here we have Garcia Manzo from 2006 in the Journal of Theoretical Biology. And what you see here is endurance world record events fit with a power law function. And you can see a reasonably good fit. So we have from 1,000 meters all the way up to the marathon. And if you log plot that, it fits very nicely. But there's a bit of a problem, or at least Garcia Manzo found a problem when they tried to extend beyond this. And so now you can see these are the power law functions for both sprinting, middle distance running, marathon running, and all the way up to and including a 24-hour run. And you can see several of the data points come off the line, and they're highlighted with these circles. And if you look at the log-log plot, you can see a clear trend in the residuals. And this, for my money, is because power law functions potentially fit the data well, but they only fit parts of the data well. And that's likely because we have these underlying exercise intensity domains in which there are very different physiological responses depending on the intensity of exercise, and that then essentially clouds the possibility of having a scale invariant power law defining them. So nice try, but unfortunately no cigar on that one. Then we bring in A.V. Hill. Now, I've already shown you this plot in a previous presentation, so I won't labour the point, but what he did was apply a hyperbolic function to it. And the reason he did that was very simple, because he could see the curve approaching the vertical on the y-axis and also approaching the vertical in relation to the x-axis. And a hyperbola seemed to him to be the best way of characterising that. And this is essentially the model that's been taken forward ever since. I find it really interesting, though, that a true hyperbola also has an opposite curve. And so there should be a speed-duration relationship on the negative time and the negative speed axis. And there's probably a bunch of scientists arguing about that curve as well, but they're doing it all backwards. Anyway, let's be a bit more sensible about this and think about where we also see speed-duration relationships, and we see them all over nature. So if you look at these experiments, you start to look at the values that you see on the x-axis, and you think, hang on a minute, this is speed of no more than 0.75 kilometers per hour, and whatever's doing this is managing to exercise for about 50 minutes at 0.3 kilometers per hour, and much shorter for 0.6 kilometers per hour, less than 10 minutes. What on earth is doing this? Well, the answer is it's a ghost crab. A ghost crab also has the same speed-duration relationship as a human, just at different speeds. We also see this in the lungless salamander, and not having lungs, of course, significantly reduces your maximum sustainable speed to about 0.05 kilometers per hour. So it's probably worth having lungs, if you can, or some gas exchange surface. You could have gills, and when you have gills, here's some data from Martin et al., where they looked at the sports science of salmon. And believe it or not, they were tracing and measuring the progress of salmon up the Sacramento River, and they've applied 3 models to predict what would happen. The first model was just an oxygen cost or cost of transport model, where they didn't have any power or speed constraints in their model. And that was what they predicted. The observed is the grey bar here, or the grey curve that you can just about see underneath the other 2 models. This model here is a critical power model. So a straight critical power model. And then the third model is a critical power model that also takes into account recovery processes. And when you have a critical power model and recovery processes, it very closely represents the speed in the upper Sacramento River, where there's very large channels and therefore not lots of rock pools and waterfalls and stuff. When you get to that point, then the models break down. But in theory, you can use a critical power type model or a critical speed type model to accurately predict the speed of migrating salmon. That gives you some degree of impression of the scope of this relationship. But back to the human. And what we have here is a paper from Romert in 1960 entitled Determination of Rest Breaks for Static Human Work. I just think it looks better if you write it in the original German. But I'm not going to try and pronounce it because I don't want to disgrace my German friends. However, the key thing here is you have this same hyperbolic function, and in this case you're looking at static work. So this is holding a contraction for as long as possible at different fractions of your maximum contraction force. And what Romert discovered was that the limiting factor, or rather the limiting level where you could sustain the contraction for a very long time, was about 15% of the maximal contraction. And that's largely because below 15% you've probably got arterial inflow and therefore you can sustain that contraction, but above that you're arresting blood flow. This was later followed up by Monod and Scherrer in 1965, and this is the curve for a static muscular contraction. So an isometric contraction held for as long as possible at different percentages of the maximum force. And again, you can see the asymptote of that relationship is, in this case, 14% of MVC, but essentially the same as Romert had found. Now, most people cite Monod and Scherrer because this was written in English and not German, but Romert does deserve the credit for discovering it first. And the B line here, this is for intermittent contraction. So this is where you contract and then you rest, and then you contract and then you rest. And so you get extra arterial inflow, and so the sustained force you can maintain, the asymptote of that force, is very much higher. And here's where the controversy comes in, because Monod and Scherrer called this critical power, but they were measuring force. And they called the asymptote critical power, being the maximum rate a muscle can keep up for a very long time without fatigue. And the emphasis there is mine, because we now know that's not true. First of all, it's not a power, it's a force. And secondly, we know that exercise performed below critical power is associated with fatigue. So we've got to be very careful with how we actually express this relationship. But above the critical power, fatigue occurs and a fixed energetic reserve is used up, and that determines the duration of exercise. That's our curvature constant, which we now call W prime, and the prime symbol there is a bit of a strange one for anyone looking at it mathematically. It's not representing a first derivative. The prime there is really just to distinguish the capital W as work rather than watts. Why we use W I don't really know, but that's just a historical hangover. And at and below the critical power, tasks should in theory be fatigueless, and the energetic reserve represented by W prime should not be utilized. Well, now we know that's not strictly true, at least in terms of being fatigueless, but I'm not going to dwell on that in this presentation. What I am going to do is go back to cycling. And around about the same time as Romert was working out his curves and Monod and Scherrer working out theirs, David Wilkie was drafted in to do some power duration relationship modelling so that a committee could set up a competition to try and stimulate man-powered flight. So there was a prize on offer for anybody who could actually get an aircraft be powered by a human pilot. And Wilkie's first task was to determine whether this was even metabolically possible. And so what he did was essentially produce a power duration relationship and then calculate what the maximum sustainable power would be. And in this case, he was arguing it's around 300 watts. And then he made some simple calculations as to what that would mean for being able to get a craft into the air. And he suggested it was just about physically possible to do so. And by just about physically possible, he really meant it, because it took about 20 years for somebody to claim the prize for this particular endeavour. So initially there was a figure-of-8 course lasting about a mile, which the pilot had to pedal around, and that was done in August 1977 by the Gossamer Condor. And then 2 years later, Brian Allen, who you can see here, phenomenally managed to get this craft all the way across the English Channel. It took him about 2 hours 40 minutes to do it, and this to me is the ultimate time to exhaustion trial, because there he is pedalling along inside a plastic bag. If he fails to maintain the rate, this thing ends up in the sea, and being in the sea in a plastic bag is not a great idea, and he managed to do it. So that's a phenomenal feat of human endurance. It really can't have been easy to do that. And the way they managed to do this, actually, in comparison to everybody else who attempted it, was they built aircraft that were large enough, light enough, but that could therefore be pedalled slowly enough that they would fly at about 9 kilometers per hour, whereas others were trying to fly at twice that speed, and it just wasn't metabolically possible to get up to that speed. So that's a little bit of interesting application of the power-duration relationship. But now from that point forward, really, and the work of Brian Whipp's group, particularly led by David Paul, we now have the 2-parameter critical power model. I shouldn't neglect to mention R. Hugh Morton's role in all of this. He did a lot of the mathematical background to power-duration relationship modelling in the 1980s and early 1990s. But nevertheless, this is the model that most people use to characterise the power-duration relationship. If you're using it in running, obviously it's not power, it's speed, so that becomes S and CS rather than P and CP, but everything else, and it'd be D prime for distance prime rather than work, but everything else is essentially the same. And of course the theory here is that you can use up a fixed amount of work above the critical power depending on what the power requirement is. That will dictate what the time to task failure is. So here we have somebody pedaling just over 400 watts, completing it in about 2 minutes, then pedaling at about 330 watts, completing that in just over 230 seconds, and then about 280 watts and 290 watts, completing that in over 400 seconds. But the area of each of these rectangles is identical and is representing the W prime, and then the critical power is the asymptote of that line, in this particular case 250 watts. Now how do we go about fitting that? Well, it's actually relatively straightforward. So what I've got here is 2 examples of how you can do it. You've got the work time model, which is a simple linear regression function. You can do this in Excel just by plotting the amount of work against time. Now if you plot this in kilojoules, then your CP will come out as 0 point something, but all you need to do is multiply that by 1,000 and that will give you the true CP. And then the W prime will also be measured in kilojoules if you plot it in this way. But here we have the hyperbolic function, so we've got time on the x-axis because it is the dependent variable, so time to exhaustion, and then we have power output on the x-axis and time on the y-axis. How do we fit this particular nonlinear model? Well, the way you do it is you can use SPSS or SAS. You could probably use Minitab, although I've never tried it. What I've done is use GraphPad Prism. So all you do is you put your data in the data columns, then you press Analyze, go to XY Analyses, Nonlinear Regression, and then what you do, you click on OK, and you then do your own user-defined equation. So click on New. I've called it critical power. So the A parameter is equal to the curvature constant parameter, or W prime. B is the critical power. And there's your equation. Y equals A divided by X minus B. And that is all you need to do to get an estimate of critical power. You need to put in some initial values, but I put in 250 watts and I put in 1500 kilojoules. Oh, sorry, 1500 joules. Don't put in 1500 kilojoules, that'd be silly. And then you fit the data. And when you do that, this is what you end up with. So in this case, critical power 334 watts, W prime 18.2 kilojoules. And that's, near as makes no difference, identical to the linear version of that, so 333 and 18.4. The differences in these parameters is absolutely trivial. But the fitting of these data is really important. Why have we chosen 5 predicting trials? Well, because that's better than 4, better than 3, and certainly better than 2. And the reason it's better is that you get more confidence in your parameter estimates with the more data points that you use. Of course, there is a limit to this because it's very difficult to get people to come in and do 10 trials to exhaustion. So you have to be, there's a little bit of compromise as to how many trials that you do, but there is a cost to doing fewer. And here is an example of that cost. Now the cost is not necessarily in the point estimate, which is what you see here. So what I've got is power output in watts against the number of predicting trials used. And you can see the parameter estimates are actually pretty similar. There's about a 5 watt drop off in this case for the 3 predicting trials. And then these 2 are essentially identical. Now, these data are from the the plot in the last slide so you can understand where the data have come from. But the error bars here are the 95% confidence intervals. Now they're so small in the 5 predicting trials case you can't see them. You can just about see them in the 4 predicting trials, and then in the 3 predicting trials they're absolutely massive. And what I've done here is I've just removed the longest trial. So started off with 5, then removed the longest one to produce 4, then removed the next longest one to produce 3. And the reason I've done that is that in the late 1990s, early 2000s, there were a lot of critical power studies coming out with 3 predicting trials, often of 1 to 10 minutes duration. And what you really need to do is at least 2 to 15 minutes duration to get an accurate power duration relationship, which also has tight confidence intervals. And really what you need to do is minimum 4, ideally 5, but obviously you can compromise those in terms of whether you need a lot of data in terms of you're doing various interventions or whether you're just doing a one-off critical power measurement. If you extend the y-axis and just focus on the 4 and 5 predicting trials, the confidence limits for the 4 predicting trials is plus or minus 12 watts. For the 5 predicting trials, plus or minus 3 watts. So these are as good as you're going to get in the literature. And these data represent those we were using to validate the 3-minute all-out test. So one of the reasons we're so confident in the 3-minute all-out test in that study being accurate was that our critical power estimates from the traditional measurement were also extremely accurate. The 4 predicting trials is usable, provided if you're looking for changes in critical power, you're expecting to see changes of bigger than 12 watts, plus or minus 12 watts. So training interventions, for example, you might expect 20, 25, maybe 30 watt improvement in critical power in untrained individuals. You could use 4 predicting trials to achieve that. Critical power, of course, is only useful if it represents something physiological. And what I'm going to do in the next presentation is go through in more detail what the underlying physiology of the critical power is. But fundamentally, it's a domain boundary between heavy and severe intensity exercise. So here's some data from one of our 3-minute all-out test validations, and these black symbols are 15 watts below the critical power, or the end test power in that case, and these white symbols are 15 watts above the critical power. And you can see above the critical power you cannot maintain a steady state, and you reach exhaustion within minutes. Below the critical power, you can reach a steady state and sustain at least 30 minutes of exercise. And that is why the critical power is important. What is critical power then? Well, it's the asymptote of the hyperbolic power duration or speed duration relationship plotted from severe intensity exercise. Fitting the power duration relationship is straightforward mathematically and logistically, but you've got to be a bit careful. You need to be able to avoid the pitfalls in fitting data. If you're using critical power experimentally, you really need a minimum of 4 predicting trials, ideally more than that, although obviously there are practical and logistical constraints to that. If you're using critical power practically or in the practical situation, you might be happy with the lower confidence in your parameter estimate, provided it gives you a ballpark figure for what critical power is, from which you can then refine it. So in that sense, it really is horses for courses. And with that, I'd like to say thank you very much for listening to this presentation, and I will see you next week.